Greetings to the viewer, this is Jashandeep Sethi right here, and in this video I'll be solving question 2 of MAT104 Endterm. So let's begin. Okay, so we have been in question 2 we have been provided with this differential equation, and the question is asking that under what conditions on the constant a, b, k and l would this ODB become exact. Now let us first understand what is an exact ODE. An exact ODE is nothing but a nomenclature which is used to refer to the exact differential of a function. So in order to find out the condition on which this ODE will become exact, let us first consider a function z of x and y, which is just a regular function of x and y. So one thing we know that dz is basically partial differential of z with respect to x dx plus partial differentiation of z with respect to y dy, and this is basically what the differential would be. Now if z is a constant, that is if we take z to be constant, then dz would become 0. Now what is the reason for taking z as constant? The simple reason is that this particular condition would suppress a 3D graph into a 2D graph, which would give us contour lines, right? So we can take this term as m and this term as n. Now we know that m dx plus n dy equals to 0, right? Now this would be an exact ODE if partial differential of m with respect to dy is equal to partial differential of n with respect to dx, right? Now how do we know that these are equal? So let us just replace m with its original term and n with its original term. So what we get is partial differential of z with respect to x first, then partial differential with respect to y, and on the right hand side if we replace n we get partial differential of z with respect to y first and then with respect to x. Now we know that this is obviously equal. So on rearranging the initial equation that we have been given, we get ax plus by dx plus kx plus ly dy, which is equal to 0. I have done nothing but simply taken this term on the right hand side, and then since this dx term would be right hand side, I have just cross multiplied it with this term and brought the right hand side term back. So it eventually leads me to this equation. Now let me just call this equation as 1. Now if we compare this equation with the equation number 1, we get m equals to ax plus by and n equals to kx plus ly, right? Now we have to prove this equation first in order to prove that this is an exact ODE. So this equation needs to be proved. So we put the value of m and n into this equation. So partial differential of ax plus by with respect to y and should be equal to partial differential of kx plus ly with respect to x. Now the left hand side, since this term would become, since it's a partial differential with respect to y, this term would become 0 since it's a constant, and this term would simply give us b. And on the right hand side, this term would give us k and this ly term would become 0. So this would give us k. So the condition on the constants a, b, k and l should be that b should be equal to k for this particular equation to become an exact ODE. Now we have to solve for the exact ODE. So let us take the equation, just give me a second. Yeah, so let us take the equation p plus integration of q dy equals to c, right? Now we'll take p equals to integration of m dx with respect to dx, and q we'll take it as n minus partial differentiation of p with respect to y, right? This will be our q. Now first we'll solve p because we need partial differential of p with respect to y. So we get p equals to ax plus by integration with respect to dx. This is what we get. So this leads us to ax square by 2 plus bxy. Now the partial differential, sorry, this was a only, I by mistake did it d. Yeah, so let me just rewrite this a. Okay, so the partial differential of p with respect to y, we are doing this because we need it in q, is nothing but bx. This term would become 0 and this term would be, since it contains a y term, so we'd simply be left with y. It contains first degree y term. Okay, so now I'll just separate this. Now if we take this partial differential of p with respect to y and put it here, we get, and we take the initial value of n from here and put it in q in this equation, then we'll get n equals to kx plus ly. This is the initial value of n that we have taken from the previous page, and this is basically nothing, since we know that k is equals to b for this particular equation to be an exact ODE. So what we'll do is we'll basically replace this case with k with b, so it becomes bx plus ly, right? And then we'll simply put this value in this equation, in the q equation. So this gives us bx plus ly, and we found out that partial differential of p with respect to y was nothing but simply bx plus ly, so minus bx. This would lead to q equals to ly. We have simply done nothing but replace the values of n and partial differential of p with respect to y, and we have come up with the q equals to ly. And here we have come up with p equals to ax square by 2 plus bxy, right? So let me just focus this a little bit more. Now all we have to do is put the value of p and q that we have found in the initial equation. So what we get is ax square by 2 plus bxy plus integration of ly with respect to dy, right? And this is equals to ax square by 2 plus, and basically it's equal to a constant only, plus bxy plus ly square by 2, which is equals to a constant c, right? So yeah, let us just give this equation a name. Let us call it function u. So basically this is a u function in terms of x and y, which is this equation itself, ax square by 2 plus bxy plus ly square by 2, which equals to c. Now what we can do is we can, since u is in terms of x and y, we can differentiate u du basically by partial differential of u with respect to x dx plus partial differential of u with respect to y dy, and this is basically the equation, the initial equation for which this is the differential equation. So if we differentiate u, since we don't need to verify, since it's not given in the question to verify, but had it been given, then all we need to do is simply follow this particular equation, differentiate u with respect to x and y, and we'll surely land up with this differential equation itself. So I guess that is pretty much it. This is basically, let me just underline this. So this is basically the final solution of question number 2. I'll just focus on it a little so it's easier for you to understand, and the second page also, right? So thank you for viewing. Have a good day ahead.